All right. So I guess I can start with some announcements. We've reached the end of Thanksgiving week. This will be the last lecture of this week, and then last week of classes is next week. My plan today is to get as far as I can reasonably to try to reveal the second project possibility by the end of today. If I can do that, that will be great, because I would like to leave that as an option for people. And if you do both, then be able to give you some extra credit for doing the second project. But to get there, we have to get through the first and follow functions and then talk about LL parsing. So that's a tall order. We'll see how far we get. So last time we talked about the first function. The goal of the first function was to find, for every non-terminal in the grammar, we wanted a set of all possible terminals that could be the first terminal in a string that is derived following any production sequence starting with that non-terminal's productions. So we found that we just end up unioning a lot of these things together. So first of S was defined to be first of S, union first of ASB, union first of capital A. And the first of any string that starts with a terminal is just that terminal. So we start with the empty string, or the empty set. And we union that with the A from ASB, and we union that from first of A, which we need to now go calculate in more detail. First of S is just itself. So a set is just going to contain itself at this point. So whatever else it has, we ignore the fact that first of S contains first of S. Looking at first of A, now we see that we can, it starts with itself, because of course it does. Union first of lowercase b, whatever else is there doesn't really matter, that's just going to be B. Union first of C, which is going to be itself. So we see that first of A is just the set that contains BC. We then can replace the first of A in the first of S with the set BC. So we get the empty set union A union BC, which gives us every possible character in this alphabet. So then we looked at this one, and we found we had some recursion. That recursion means that we said first of S is defined as first of S union first of SA union first of B. The first of SA starts out with that capital S, which just reduces down to first of S. So we can see that that self-reference doesn't make it possible to start with a lowercase a. So that means that the only string that can be accepted by this grammar has to start with a B. There is no way for a string to start with an A, and you can logically go through that and verify that for yourself as well. But then I ended last class saying that lambda makes life just a little bit more complicated. So what are the rules that we're going to use for lambda? If we see a production with just lambda on the right-hand side, the first of lambda is lambda. But if we have first of some non-terminal, and that non-terminal can derive lambda, we have to also now think about any productions that use the next symbol in that production. What does that mean? How does that work? Let's give you an example. So here's a grammar where the non-terminal capital B can just derive lambda. This is especially challenging because now we have to consider, well, if B can be empty, what happens when we have the S arrow capital B capital A D production? What does that do if that B can derive lambda? Well, it means we have to consider the first of A capital A as part of that S arrow, because since B can derive lambda, we will actually need to consider that. Does that make sense? Yeah, let's go through and take a look at kind of the logic of why that works. So we can imagine that two possible derivation strings here. We would have S arrow, capital B, capital A, D, arrow. Now this capital B is going to become the first sequence. So we still have lowercase b, capital B, D, capital A, D, coming back from the capital A, D from here. And we will expand this B to be lambda now. And so we end up with B, D, and we'll just turn this A into a D, D. So we have an example where this capital B can produce this B. But there's another possible sequence where this B becomes lambda. And you can see now that S has derived capital A at the start of it and not capital B. So we need to consider the first of A in a sequence where this B becomes lambda. Because according to the way that we had tried to do this before, we had only considered first of a terminal and a non-terminal. And so if we didn't do that for this lambda, we would say first of B is only lowercase b. But we can see now that we have a couple of choices. I'll even expand this into a couple of choices where this A becomes C capital A or D, which ends. And now you can see we have two different options here that can start a string directly from this capital B that we wouldn't have been able to identify if we didn't anticipate and see and check this lambda as a possible production. So this comes because of these two sequences right up here, where this capital A is immediately derived after the B. So if anywhere in this grammar we see a non-terminal that could derive lambda, we now have to move and check the next symbol, in addition to checking that symbol because it may not be lambda. Excellent. Let's go all the way over here. So with that said, let's generate the whole first table for this grammar. So as always, we start with first of S, algorithmically. Maybe it's easier to start with first of something else if you're building this on paper for yourself, but we will start with first of S and just kind of recursively go. We will see that first of S depends on something. And so we'll go answer that question and then return from the recursion and be able to answer fully first of S. So we start first of S. We start with all of them being empty for now. We can see that first of S depends on first of B. So if you do see that, you could add lowercase a to the set of first of S and then recurse on first of capital B and try to figure that out. So intellectually, since we're not writing the program for this, we'll start with first of A and first of B. So first of A and first of B, first of A is just the lowercase c and lowercase d. So we union those together and get the set that contains C and D. Great. First of B, we see that we're going to include the lambda now. And this is algorithmically how we're going to see how we need to go look at the next character. So we're going to add lambda to our first of B. When we calculate first of S, now we're going to say first of S, of course it contains itself, first of lowercase a, which just means we're going to add that, first of capital B. All right, now we're going to have to recurse and add everything from B to A. So calculating first of capital B, we know that's already B and lambda. So when we see that in the first of B, since B can derive lambda, we also have to consider the next character in that sequence. So this is why you can't just say that, great. You take the first character here and that's it. You actually have to take the first of this entire string, because if this now can derive lambda, then you'll also have to consider this. So we see when we do that lookup for first of B, that it actually contains lambda, so we now need to look at the A. When we see that, it's important that we store all of this information so that we can go calculate it. If you're doing it on paper, it's a little bit less important that it is in exactly this notation, but it is still better to be complete than not. All right, so we see now that we also need to union with first of capital A, which was that second character in BAD. So now we can see that the entirety of first of BAD is B and C and D. The B comes from the first production in the B arrow. The C and D come from the fact that we had to look at capital A because there was a production in first of S that had us looking at first of B, which could be lambda. So this whole process can become recursive at a pretty interesting level. There's a number of, there's lots of depth to that recursion, potentially, depending on the grammar. How many, this is only for a single case of this capital B. You can imagine a grammar where there's a capital B somewhere in here, followed by a capital S, followed by, you can get into some interesting recursions that you will need to be able to escape from. So note that you don't want to get into, you can imagine that. Like what would happen if we had, how can I create that infinite recursion? It's easy enough if we just do something like, or capital B, lowercase a. So if B can derive B, first of B is first of B, because it can be lambda, we now need to consider the next thing. So that could be a B. So now we have to continue to check this process. But imagine if it's now something like this B goes here, can derive this A can now derive or BS B. Who knows? But now this B refers to this A, which refers to this A, which can now be this B, which can be lambda, which can refer to S, that can create an extra A, that can, you can see this creates an infinite recursion that we would have to escape from somehow. And that somehow is that we would recognize that we're answering the problem first of S. So because we're storing this, then we want to be able to make sure that we don't actually go and calculate first of S, because we're already calculating first of S. We never want to recursively ask the same question we're already asking. So as long as you have that information, store it in a table, a globally accessible table somewhere, so that you can make sure I should be answering that question, or you can pass it in as a parameter, something that allows you to check. Here are all of the questions that I'm currently in the process of recursively answering. Don't start any of those processes over again. Then you will not get into an infinite recursion. All right, so now we'll define fully first of S for this grammar to be first of S union first of the first production that S can produce, union the second production, and then we see that recursively we can go answer first of capital B. Now we have a full set for that BCD. So we can see that the first character in any string in this grammar could actually reasonably be A or B or C or D. Excuse me. How is that? Does that feel all right? It's because we answered that question recursively. That's a great question. So it only depends on the first of B here, but when we look at first of B, we saw that it included this lambda. So this lambda tells us that we also need to consider the first of the A here. So we calculated first of A to be this C and this D. So if we're looking at where the answers come from in this B was responsible for this B, which was responsible for this B. This C and D were responsible for this C and D, this C and D. So we queried this by seeing this lambda. They said we had to look at the A, so we looked at the A here, and then the other option for the lowercase a came from right here. So we can see that there is a way to derive A and B and C and D directly from S. But it relies on seeing that this B can derive a lambda, which means that we need to check the next non-terminal. Did I see your question? Awesome. It may help, especially intuitively, to go look at this process in the other direction. So we're going to kind of backtrack. Once we have a first function, we can verify its correctness to make sure that we didn't skip anything, miss anything, etc. So for each element of first of S, shows some derivation where we end up with a string that begins with that character. So since first of S could produce strings with A or B or C or D, now we can just come up with this sequence of derivations. S arrow A capital S C shows that we could derive a string that starts with an A. If those non-terminals get resolved to something, great. Doesn't matter. We have a derivation that now can start with an A. We're done with the A. The next one, we found that we can show a string that begins with a B. And again, it's perfectly fine to leave those non-terminals in there for now. It doesn't really matter what they eventually terminate into as long as they do terminate. And again, you can show strings that start with C, strings that start with D. Then you can go on to first of A and say, all right, what was in the set first of A? Well, there was C and D. So we have a couple of derivations here that show starting with the non-terminal A, we can end with a string that starts with C and a string that starts with D. Same thing with first of B. For everything in first of B, we can start and show a string that begins with that terminal. Note that we can also do lambda directly, but that will only ever be the case when you have something that there's no reasonable string that begins with lambda and then moves on to other things. So if you have a lambda, just derive lambda and you're done. So this is the first function. This is the time to clarify anything that you are fuzzy about, because we're going to be using the first function in some additional rules as we talk about the follow function. Any questions about the first function? Do you feel like you understand it? Anything that I can do, more examples, something that will help you to better understand it? All right, on to follow. So just like the first function was defined to be given a non-terminal, we wanted to find the set of all possible terminals that could begin a string with some derivation from that non-terminal. The follow function is defined to be something very similar. It's saying, when we have that non-terminal, what is the set of terminals that can immediately follow it? So you can imagine what happens after we see a capital S. Once we resolve that to be whatever it is, what is the set of terminals that could immediately follow whatever that derivation ends up being? So why do we care about the follow function? This helps us to be able to quickly choose which production to expand. We'll do a lookup into the string that says what comes next. And then we can, whenever there are choices for which expansion or which production to apply in a particular place, we can query the follow function to see which of those paths to go down. Because as nice as it would be to have a non-deterministic system, we have deterministic systems. So we actually have to make those decisions. We will use the $sign to denote the end of a string. This would say that what follows this non-terminal could be the end of a string. It can appear in any follow function saying that exactly what I just said. It could be at the end of the string. So we know that since S is the start non-terminal, that by definition, what can follow the start non-terminal is the end of the string, if that makes sense. Basically, S represents the entire string of everything that is in the language by some set of productions. So what follows S naturally includes that end of string. So we're going to go through the actual algorithm, and the way that the book uses it is they use V and W. Do note that these V and W can be any terminal or non-terminal. That'll help this make a bit more sense. So we start by adding $to follow of S. Then we're going to be looking, saying, go through all of the productions for all non-terminal arrow something. And again, that V could be any terminal or non-terminal. So this is just going through every production. We can say that follow of A is in follow of B. And this capital B now is any non-terminal. So if we have a terminal non-terminal pair or a non-terminal non-terminal pair, we'll be looking for those pairs and adding follow of A to be B. Does that make sense? Why does that work? So we have some A arrow something. It just matters if there's something that ends in some non-terminal. I'm just going to call this N rather than B. Whatever comes after this can also come after this, because this can end this. So let's say in some derivation, we end up with capital A, lowercase b. When we expand this capital A, this could eventually turn into blah, 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 capital N, B. So because B can follow A, B can also follow N, because we have a derivation here where N is at the end of some production that is an expansion from A. So we can say that whatever can follow this can now also follow this. Did that help? Excellent. All right, now if we have something that ends, so this is, we have some A that now, remember, B's and W's can be any terminal or non-terminal. So we have some non-terminal in the middle of some production. So we can see that first of W minus lambda, because lambda here doesn't matter, is in follow of B. So whatever this token can produce at the very beginning naturally has to follow this character, or can follow this character. So it's important to have the first function to be able to reference as part of the follow function. If lambda is in first of W, then whatever could follow this character A could also follow B, because this is now the end of the string. So if this can derive lambda, that means it's possible to not have this at all, which puts us back in this situation where follow of A is in follow of B. So that's just a special case where if this can go away, we end up back here. So those are some important rules. But that's it. That's the entire follow function. I think it helps initially, rather than following the exact rules, to just think about it in terms of logically what set of terminals or non-terminals can follow a particular non-terminal. And you'll probably derive this algorithm as you go through that logical process. You'll see that these are all of the cases that you need to be able to do that. So let's go through an example. Here is a fairly simple grammar, but now we want to know what is the first of it. Sorry, the follow of S and the follow of A. So go ahead and give this a shot. And then let me know once you've reached a point where either you are stuck or you think you have an answer. Either one of those is perfectly okay. You have the grammar written down. I can go back to the rules if you'd like. You're going to start by adding dollar to follow of S. Now to figure out what could follow S, what could be at the end of S? So we're going to look for all pairs of capital S followed by something. So we can see that once we finish figuring out what S is, B could follow S. But since S could immediately derive A, we know that whatever follows A could also follow S. As an example, we could expand this to be S arrow A, which becomes B A. Actually, no, it's not going to work. We need to derive the first one first. we end up with ASB, which now becomes AAB, which now becomes BAA. But note that all of this followed this S at the end, where the S just expanded into a bunch of other stuff, but what follows that is still the B. Is there a way to get an A to follow that S? Let's see how it works. So we see that S appears on the right-hand side of S in the ASB. So we're going to add B to follow of S because it follows S. So far we have follow of S is dollar and B. We also see that A appears on the right-hand side of A and this B capital A. So for the right-hand side of this, that's much easier. We can see that what follows the A in here is a lowercase a. So we want to add A to follow of A. For the former, anything that follows S can also follow A, if that makes sense. So we're going the other way around now and saying that, great, since A can be immediately derived from S, whatever can follow A can also follow, whatever follows S can also follow A. So, and this says add everything from follow of S to follow of A. So now follow of A is A and B and dollar. Does this make sense? This is why it was a struggle to make anything else follow S, because it's not possible. On the other hand, if we end up with an A, there should be a way for what's after that to either be a lowercase a or a lowercase b, or the end of the string. So again, if we wanted to verify this follow function is correct, we should be able to have some derivation starting with just capital A that says we're going to eventually derive something that after that is A or B or dollar. Can we do that? It involves starting with the S. We can't just start with the A like we could with the first function. So let's start with S and see if we can generate something where eventually what follows that A is each of these characters. So the easy one is the dollar sign. How could we proceed from here such that we derive an A, and at the end of that is the end of the string? Well, we just go straight to the A. So the expansion from this was the C. What followed this is what follows this, which is the end of the string. So that's the end of string example. Now, how could we get the follow being A? So we need to derive this, right? Because that's where that happens. So let's start with S. We can go directly to A. We can now change this A into B capital A. And now what follows this A, whatever this happens to be, let's just go directly to the C, B, C, A. What followed that A was an A. And then how do we derive a B? Well, we go from S to A to, I think we actually want to do this first. S to ASB. Now we go to the A capital AB, and we see that what follows the A is a B. So it doesn't matter what we do from here, we can make this the C again, and what follows that is a B. So now we have all three examples of what followed, whatever we did to the A from there. It doesn't really matter, but we constructed something that says what follows the A is the end of string, what follows the A is an A, what follows the A is a B. So that tells us that our follow of A is correct. Yeah. What it doesn't tell us by going through this is if we're missing anything from follow of A. But at least it guarantees that everything that we've added to follow of A is correct. There's some string that we could derive for it. All right, let's have another example. And now it gets a little bit more complicated. We're going to use our second example now, where we include a lambda. So now, given that, what is everything that is in follow of everything? If we go back to our algorithm, that might help us out a little bit. So let's go ahead and give this a shot and see if we can come up with an answer. So again, let me know whenever you get stuck or if you end up with an answer, and I will go through it. Okay, so follow this, we know, yeah, has dollar, because we know that it always has to, that always has to be the case. And then we know that S can end in, or what follows S can be, we see it here on the right-hand side, C. So that should be the next thing we add to follow this. So this is all we know. This is all of follow of S, which is nice. It gets a little bit harder when we start to think about follow of A. What can follow A? So we see A in the right-hand side of which productions? We see A is on the right-hand side of A, capital SC. So now we need to calculate first of capital SC and add everything from first of capital SC to everything that is in follow of A. Because what S can begin with can follow this. So the first of S is in the follow of A. If that makes sense. It really should be the first of SC because maybe it's possible that S could derive lambda and we have to add the C. But in this example, S cannot derive lambda, but it's important to consider that that may be the case in general. So what was first of S? What is the first character of some production involving S? Well, we calculated this before, but S can derive A at the beginning. S can derive B, which can derive B. S can derive B, which can derive lambda, which means we need to calculate the first of A, which could be C or D. So everything was in first of S. So we're going to add A and B and C and D, all of which join follow of A. We still have to go consider every other place that A shows up on the right-hand side. So it's on the right-hand side of capital B, capital AD. So first of this lowercase d is just D. We add it to follow of A. It's already there. A is also in the right-hand side of C, capital A. Since it's at the end of a right-hand side, we add everything from follow of A to follow of A. That also does nothing. Questions on how to calculate follow of A? So we care about some derivation where we end up with an A, and what follows that A is whatever. Doesn't matter, but we start from the start non-terminal S. So if we derive S arrow A, capital SC, we can see that if we go down this road, what follows this A is naturally what begins this S. Anything that begins this S can follow this A. So if we wanted to calculate anything that could follow a capital A anywhere in the grammar, we would have to consider this possibility and add everything from first of capital SC into follow of capital A. As we do that, we end up with 4 branches, which is the same 4 branches that we saw when we calculated first of S a while ago. So that naturally has to add everything from first of S into follow of A. Does that make sense? Yeah, let's draw it out. So we're interested in derivations where after we calculate out this capital A, what are all of the terminals that could follow it? So let's actually, I'm going to write this out and then I'm going to derive all of the possibilities. So we have S arrow, A, capital A, S, C, and I'm going to draw 4 arrows as the 4 possible directions that we could go from here to generate something that follows that A. So I'm going to leave this A as capital A and just move on with this capital S to show what could follow this A. So if we take this A and we make it something like, or sorry, the S, we can turn this in the S into, all of these are going to have A capital A at the start because we're modifying the S. So this S could become A capital S C. And now we have an A following this capital A. Here, we could have this S derive capital B, capital A, D. And that's just expanding this S into that. Sorry, this S into that. So then this B can become lowercase b, capital B, D. A, capital A. Now this B becomes B, capital B, D. And then we still have capital A, D, C. And now we can see that we've derived a subsequence here where the lowercase b follows the capital A. Now we can do the same thing if we do the capital B, capital A, D, C. But now we're going to turn this B into that lambda. So here we have A, capital A, D, C. And here we have A, capital A, D, C. But now we're going to expand the A that followed that A into this associated C and D. So we still have A, capital A, but now this second A becomes C, capital A. And now we have a C following an A. And here, the second A is going to become this D. And now we have a D following an A. So the idea is just to algorithmically go through this process and figure out what are all of the terminals that can follow this particular non-terminal. And so all of this information was actually already calculated. We didn't have to go through this work again. This was all contained in first of S because we did all of this work when we said, all right, what are all of the terminals that could be at the start of a production of S? Because that's what we did here, right? We took this S and we broke it down into a bunch of different things for that S. But what began after this A was what was at the beginning of this S derivation. So if we've already calculated the first table ahead of the follow table, we don't need to go through this work as part of the follow. We just do a lookup into first of S. And first of S is already going to contain that A, B, C, and D. So all we have to do is take follow of A and union it with that. Basically adding this to that. Whatever we've calculated so far, take this first of capital SC and union that to follow of A. Does that make more sense? Excellent. Well, we are out of time, which is probably good. I want to pick this back up in a way that will help other people to get through this confusion as well. So we will pick this back up after a long turkey break. But I hope you have an excellent Thanksgiving. Hopefully there aren't too many people and the people aren't overwhelming. And I will see you back on Monday. You can look for the extra project over, I guess, later today, but I don't think we're quite at a point where you'll be able to make significant progress with it. My recommendation would be try to crank out the CYK if you have not done that already. All right. Are there any other questions? Thanks, and I'll see you on Monday. Take care.